Greetings and welcome, friends. We're taking a look at page 489 from the homework. We're talking about specifically the factor theorem. And this actually, oh man, we started off with a doozy. The direction said, given a polynomial and one of its factors, find the remaining factors of the polynomial. Some factors may not be binomials. So here I'm told that this is a factor, which, by the way, question, if this is a factor, which x-intercept does that factor give us if I set that equal to 0? This particular factor would represent an x-intercept as well. Do you guys know what the x-intercept would be?
2/3.
Yeah, it'd be 2/3, 0.6 repeating. Because if I set that equal to 0, I'd have to add 2 and then divide by 3. Correct. Now, this one, in order to find our depressed polynomial, I just want to point out synthetic division might not be our best choice because of this leading coefficient of 3, which you could still use synthetic if you just divide everything through by 3, but I don't know if that sounds like fun. So I'm gonna go with long div. Did anyone get it successfully with synthetic? So let's see, 3x minus 2 is our divisor. Our dividend is 6x cubed minus 25x squared plus 2x plus 8. No placeholders required here. And let's see, divide leading term by leading term. 6x cubed divided by 3x is going to be 2x squared loop-de-2 almost. Yeah, that's a loop-de-2, I'd call it. Multiply, that's 6x cubed. And minus 4x squared. Subtract, that cancels out. That's going to be negative 21x squared with the whole double negative thing going on there. And bring down the plus 2x. Divide again, leading term by leading term. That's going to be what? Minus 7x, if I'm not mistaken. Right? Multiply is going to be negative 21x squared. And plus 14x. Subtract 2 minus 14 is negative.
Read the 14.
From multiplying this and this.
I don't get
Yeah, I would recommend doing some practice with it. Then that'd be a good strategy. It takes a little while to get used to it. Bring down the 8, and then divide one last time. Divide leading term by leading term. That's going to be negative 4, better yet, negative 4, yeah. And negative 4 times 3x is negative 12x, and negative 4 times negative 2 is positive 8. And I get a remainder of 0, which tells me that this is, in fact, 8 minus 8, because it's the subtract step. This is, in fact, a factor of this, right? Because the remainder is 0, it divided in evenly. So that means my depressed polynomial, g of x if I want to call it, or whatever, would be this quotient right here. So 2x squared minus 7x minus 4. Now, if I had some good guesses as to what like the, some other zeros or factors would be, that would be a good thing to check out. However, I kind of don't necessarily have any good guesses. We'll actually learn some strategies later to find those later on in this chapter. But this is a quadratic, and if it is further factorable, well, I know how to factor quadratics. This would be an AC method problem here, right? So AC is negative 8. Find the factors of 8 that subtract to be 7. Well, that looks like 1 and 8. Do the old split the b term, friend. So that'd be 2x squared. I'll do an x and an 8x and a minus 4. And what are those signs going to be? They're different because they multiply to be negative. Yeah, minus 8x and plus 1x, right? Because they have to combine to be the more negative 7, right? So the more influential one had to be negative. Now I do the old factor by grouping. First one I could factor out an x, and I'd get 2x plus 1. I'm just going to cruise through this. Factor out a -4, and I'd get 2x plus 1. What do you know, Joe? And I'd get my two other factors are going to be 2x plus 1 and x minus 4 are my remaining factors, right? And I could have actually considered either of those individually as a further depressed polynomial. Just for funsies, I know we didn't have to, but let's graph this. Yeah, I'll be right back on that in a second. For funsies, 6x cubed minus 25x squared plus 2x plus 8. All right, so here's our cubic function. It's got a positive leading coefficient, so you guys, of course, would have known the end behavior on that. You guys are that good. I know it, I know it. Let's see, let's do a rectangular grid, and we'll scale this down a little bit. So yeah, you can kind of see that shape right there. And the factor, or the x-intercept that we knew, would have been the one occurring at the 2/3, right? That's what we had mentioned earlier. Joey was able to deduce that, right? So 2/3 is the one that we would have known. And now let's graph actually the depressed polynomial, which was the 2x squared, x squared minus 7x and minus 4. And notice, behold, what does it have in common? Yeah, it shares some x-intercepts with it, right? Isn't that good stuff? Let's see, I'll even make that like a dashed line. Bam. So there we go. So it actually shares some of the x-intercepts. And as I said, we ended up factoring the depressed polynomial, but if we were to divide it, you know, by x minus 4, if I happen to suspect that, like if I had this graph, I would have been like, seems like it has another x-intercept at 4. That means x minus 4 is a factor. Let's divide by that to find the further depressed polynomial. So if I graph 2x plus 1, for instance, that's going to have this other, the last remaining x-intercept there, if we were in fact looking for it. So yeah, so kind of cool stuff. Let's see, this color I'll make red. Bam, there we go. Look at that thing of beauty. Thing of beauty. Here we are. I'm gonna put a snapshot right here. Whoa, I think it'll barely fit.
Now what if you graph the x minus 4?
If I graphed the x minus 4, I'd actually have a line that would cross right there, and it would have had, that would have contained the other x-intercept. So kind of a cool situation, relationship between polynomials and their depressed selves. I think it's kind of neat. 35 is the same kind of problem, but a little bit trickier, only because of the fourth degree. How many x-intercepts could a fourth degree polynomial have? As many as 4. Could it have less? Could it have none?
No.
Yes, it could, because the end behavior for an even degree is the same direction, so it actually could possibly never have to cross the x-axis. But I'm doubting that's the case, considering they claim that it has a factor. So let's divide by that, and this time I'm going to do some synthetic. Oh, I need a squared term, don't I? Placeholder. What? I could see that throwing people off right there. So let's add and multiply and add and multiply and add and multiply. What? Oh, 0 times. Yeah, sorry. Not even. Good save, friends. And add and multiply and add. Bam! And hey, what do you know? Remainder 0. That's good news for us. That means that this truly is a factor according to the Factor Theorem. Good stuff. Also, that means -2 is an x-intercept there. So, question, what is my depressed polynomial g of x? X cubed minus 8. What? Crazy sauce. So you might look at that and then wonder, well, I don't know how to factor that, really. Although you might look at that and then be like, wait a minute.
Why is it x cubed?
Because this is in the cubic slot for those, right? This would have been my constant. This would have been my linear. So there's 0x. this would have been my quadratic, so there's no x squared, and then x cubed like that. So good question, good question. So a cubed minus b cubed, if I recall that pattern, difference of cubes, it's going to be a minus b times a squared plus ab plus b squared, I believe, if I'm not mistaken. So I actually could factor this using some of my older techniques. So a is x, b is, what is b? I'll just call it positive 2 because my formula already took account. Because what cubed is going to be 8. So 2 cubed is 8, and that's how I figured it out. Or the cubed root of 8, you could have asked that as well. So if I factor this, I'll get g of x is equal to x minus 2 times x squared plus 2x plus 4, if I'm not mistaken. And now you might look at this and assume that that could be factorable, but typically this pattern, this part of the pattern is not factorable. If there was a 2 here, it actually would be the perfect square trinomial pattern, but it's not. But it's typically these are very rarely factorable from this point. So it looks as though these are the remaining factors. Let me just graph a couple of these for funsies. But yeah, so actually, well, before I say that, I would have been glad if you got the depressed polynomial here. I would have understood if maybe you didn't remember quite how to factor that, but we get to start.
Graph them like this on the test?
No. Well, yes, with today's skills that we'll be learning, we will. Yeah, the graphing, I'm just using technology to just, I'm using this only to build more connections for us. So you at this point wouldn't know how to graph. But today we're going to talk about graphing, which is good, with some limited abilities. So let's see, I graph this. So this is a 4th degree by the looks of it. Let's see, rectangular. So notice it's not quite parabolic. Actually, how many bends would you classify this as? I would say just 1. Right? There's definitely that little dimple that it's got going there, but it never actually started increasing. It was just decreasing less quickly. Yeah, it looks like a weird nose. Okay, I could see that. Let's see, I'll hide those guys. I definitely, weird nose, of course. So let's graph the depressed polynomial. That was x cubed minus 8. So that's a cubic, sorry. How many x-intercepts can a cubic have? 3. Now, which of the x-intercepts did I know I had? Negative 2 is the one I knew I had. So this one must contain the other x-intercept. Now, this could have as many as 3. It could also have as many as 1, being an odd degree function. And bam, there you go. What do you know, Joe? What do you know? Let's see. So let's make that medium. We'll change its color. Bam, line style, dashed. A little bit of dash there, right? So you can see that it does in fact have the remaining x-intercept, x cubed minus 8. Now actually, if I wanted to find that x-intercept, this equation actually would have been easy to solve. If I did the classic x cubed minus 8 equals 0, notice that I actually could solve that rather quickly. Let's see, I would cube root both sides. We don't do that often. And I would have actually gotten x equals 2. So it's actually solvable even prior to it being factorable. Which the fact that x equals 2 is the remaining factor, and I also had it here, what does that tell you regarding this and the x-intercepts that contains?
It doesn't contain?
It doesn't contain any real x-intercepts. In fact, if you tried to solve this setting this equal to 0, you'd have to use completing the square quadratic formula. You'd find that it gives you 2 imaginary answers. So it turns out this is the only x-intercept we actually cared about. Let me graph, the x minus 2. x minus 2. That's just going to be linear. Bam, that shares that. Not too crazily. And just for fun, I'm going to also graph this, the x squared plus 2x plus 4. X squared plus 2x plus 4. Now, theoretically, we're saying we've already found all of our x-intercepts. This shouldn't contain any. And behold, it doesn't. All right, it only has imaginary x-intercepts. And what's interesting is it contains the remaining 2 imaginary x-intercepts that all the way back at our original problem. This one also has 2 imaginary x-intercepts, right? Because we knew that this had as many as 4 solutions, but we only actually ever saw 2 of them, right? So we knew that it did have to have, well, actually, eventually we'll know. I know, but later this week, you guys would have known that it had 2 other imaginary ones. So good stuff, good stuff. Not bad. The extra factoring stuff is definitely a little tricky. I imagine that 30, is probably equally tricky. Was it 37? But yeah, you can see the 2 x-intercepts there. Thing of beauty. Thanks for watching, internet friends. Have a great day. Bye-bye.